Okay. Hopefully we can just share it. See if this will work, because I'm going to be able to share it. Full screen. Great. And I can see that, so I'm assuming everybody else can see it. So I have just thrown together like a little overview of pre-processing intro. I'm not going to go into too much detail today. It was mainly like to introduce people who maybe have not seen any of this. That's going on. Oh, got it. So we can see like chats, right? So if people have questions, like you can put up in the chat. So this is, I'm kind of gearing this for people who are like new to neuroimaging. Would you say that's a good place to start, Lucina, with this?
Yeah, I think so. I mean, the idea of just for people who are showing up for the first time is that we want to do a series of workshops, maybe once a month, depending on how much interest there is, but a series of intro to MRI data analysis. So it's fine if you're a complete beginner. It's fine if you're further along too. But basically a place for you to come for asking any questions, no matter how basic. This is a place where you can come and sort of get some feedback.
Yeah. So so I'm gonna like jump into this. So this is like the beginning and the ending of neuroimaging in terms of in typical. So I'm just going to be talking about time series data, not any type of like diffusion, because I know Jason, like you did a little introduction of like process or using DTI Studio, DSI Studio, but like not necessarily the pre-processing. I'm not going to be talking about any like type of structural imaging or any other exotic methods versus just like the bread and butter of time series analysis and like what do we do to get it to the point of being able to do analysis. So in a typical type of functional imaging experiment, we take a whole bunch of volumes of data of the person's brain. So I'm just showing some umpteenth number of volumes that are acquired at some regular interval. And we want to be able to take that data and turn it into some sort of statistical image that we can then write papers about. And so in this example, what I have here is a whole bunch of data that's been pre-processed somehow. And I'll go into like what we talk about, what we label as pre-processing. And I'm turning it into what's called a resting state analysis, where we've dropped a seed into the PCC. And this is showing like all of the regions that are connected or correlated to the posterior cingulate cortex. So what I want to talk about is what is in this pre-processing like red arrow that then leads you to statistics. I'm not going to be talking about any type of statistical analysis versus just like how do we get it ready for the statistical analysis. So when we acquire data, lots of things can happen to mess up your data or to change your data. There can be issues with the scanner, such as like there can be a amplifier could like happen, something could happen to an amplifier that could result in like either a spike in your data or a dropout in like some signal. The participant can move because they're in there for a long time, their head is moving a little bit, they might be moving their legs, which translates up into moving their head or their shoulder, things like that. So like movement is a problem. When we acquire these time series data here, we don't acquire each volume instantaneously. It takes a finite amount of time to acquire it. So when functional imaging first got started, it would take 2 to 3 seconds to acquire a whole brain image that would be sensitive to these types of activation studies or these resting state studies. Nowadays, with more modern systems, we can go a little bit faster, but it still takes on the order of about a second to acquire the whole brain, which means that if we're trying to understand, like I'm going to say neuronal firing that gives rise to what we call the Bold effect, the timing of that activation in your head is not synced up necessarily because there's like delays due to like when we acquire the data. And then There can be magnetic field distortion. So the magnetic field is extremely uniform, but once you put in an object in that magnetic field, it distorts the magnetic field. And especially it will distort the field around different structures in your brain or in your head. And then the final, I'm going to talk about a little bit, is that when we want to do some sort of like group inference, et cetera, to say like everybody processes faces a certain way, or everybody's like doing a motor cortex activation in a certain way, everybody's brain is different. And so where I activate in my head and space with respect to like face processing or my motor cortex isn't necessarily going to like say line up to where like Lucina's brain is doing it, because our brains are different. They're just shaped slightly differently. The general structures are there. If you've all taken neuroanatomy, the general structures are there, but there's displacements like just because of individual differences. So these things happen, and we have to sort of like remove these things to be able to get to a level of doing statistical inference. So like I said, with the scanner, so there could be some issue with the hardware, or if the person moves a lot, that can also introduce some sort of like artifact in image brightness. And so we need to be able to identify those and remove those. So that's one of the things that we worry about. And let me just like add a little sidecar here. I'm going to be talking about these maybe in I'll be presenting these in a certain order here, but order can also change in terms of how you take care of things. And I'll talk about that a little bit once I show like the whole order again. When the person moves, each volume that we acquire is not going to look the same as the prior one, like structurally. And so when we're imaging, we're sampling a specific spot in space versus a specific spot in their brain. So that if you're trying to image, say, some activation in their motor cortex, that piece of motor cortex is moving around in space. And so if we then try to do some statistical inference of it, that piece of cortex has moved such that the images just don't line up, such that we can't do any type of signal averaging or doing something like a general linear model to be able to understand the activation there. So there's that issue with the movement. And then if at some point we want to make all of our brains look the same, we needed some high resolution image to help guide us with that. And if the person moves with respect to when we acquire that high resolution image to when we acquire their time series data, that is also a place that we have to take care of, like removing that movement. And then, and I'll talk about in a minute, the distortion that happens due to the changing magnetic field. If the person's moving, that distortion can also change with respect to where they are in the magnet. So then when we acquire these data, they're not acquired instantaneously. Older versions of acquiring data is that you would either potentially acquire the data from like the bottom of the brain and go like slice, slice, slice. So we're taking 2D slices of the brain. They're typically like back then, like 3 to 4 millimeters thick. And assuming that like the person's not moving, just think about like you're slicing up a cake and you keep resampling that same cake, or you might do it from the top to the bottom. Other ways are called interleaved, where it will acquire, so like the odd number slices, so 1 through say 39 if you have a 49 slice acquisition, and then 2 through 40 after that, going every other slice. Or in more modern systems, instead of acquiring a single slice at a time, we now acquire what's called multiband or simultaneous multi-slice, where it might acquire 2, 3, 4, 5, 6, 8 slices simultaneously. And then it'll disentangle them. So it'll sort of like go like slice 1 and then slice 9 and then slice 17, etc. Might all get acquired really quickly together, and then it'll shift up and then do that next set. That's an interleaved, but it still is a little bit more complex interleaved because they're being acquired simultaneously. And then using math and exploiting some physics, those images get disentangled and result in like a nice volume.
No, can we go
Yeah.
back on it? So I know everybody's using multiplan nowadays, but we still use some of the sequential stuff for the public data. And then a leave. Can you speak to why people would do sequential in their leave? Was there a reason, or is that just scanner preference, or is there an advantage?
That's a really good. So one sequential, I think, is probably I misspelled bottom. Sorry about that. So it was like late when I was typing these up last night. So in the past, like when I was like on a GE system where we were doing like spirals and we were like doing just like sequential go up. You'll see sometimes actually in interleaved that what would look like maybe an image artifact that you can actually see every other slice in a sagittal profile. Some of it could be due to like how well you can excite a slice. So the slice profile, if the slice profile is not very sharp, then if you go and you acquire, like, say, sequentially my thumb and then my index finger, but if the thumb doesn't have a really sharp slice profile, it'll actually excite some of this slice, which means then if you go immediately to excite this one, you aren't quite getting as much signal as you're expecting. Okay, so if you go every other, you sort of like let these recover a little bit. There's still like it kind of muddles the signal to begin with. So whenever you're doing slices, you're always exciting a little bit of the other slice. And it could be also due to gradients, how fast gradients could go. Spirals are typically very soft on the gradients because they're never doing anything super sharp. There's like really gently changing the strength of the gradient versus in EPI imaging, which is what we typically use, is it's switching gradients very fast, and that can cause some bleed over as well. So, okay.
I remember so at the scanner at Stanford, they used Gary Glover's spiral and out. And the downside that no one ever talks about is that if you stop halfway in the middle of the scan, it actually doesn't write out any of the volumes that you had collected in it. Whereas like in an EPI, if you stop, 4 minutes into a 10-minute scan, you still have the 4 minutes. I remember that as being, I don't know if things have changed in spiral world, but
that just has to do with like the P file, what's called the P file that's collecting. It just matters on like, again, like how you abort the sequence. So the spiral method is acquiring just pure k-space data that has to get reconstructed offline, where when we're doing EPI or SMS EPI, the reconstruction is actually taking place inside the MR system, and it's not taking place like inside MATLAB or whatever. So the data are being written out to the reconstructor, so like a slice at a time, where in the sequential it would like write it to a big buffer, and then that buffer would get dumped to disk. And so that's why if you abort it with the spirals, it would not write out that partial, because you just like telling the program to stop. So but a lot of places, I don't know that many places that are there are some places that are looking at doing like SMS spiral, because spiral results in a sort of like nicer artifact versus the EPI artifacts that we see, which I'll show shortly, which is like this. So when we acquire the data, unlike say this anatomic image that's sitting underneath this activation map, which is like not really distorted, etc. That image, it takes like 8 minutes to acquire a nice high resolution T1 image, where like we see the coronal, the axial and the sagittal view underneath this activation map, where when we're acquiring the activation data, the data that are sensitive to activation, the EPI bolds, those are acquired so rapidly that there are artifacts in the data that we don't remove because we're acquiring it very quickly, and the bold signal needs to be sort of like in the same class of artifacts as like the big artifacts that we want to remove at some point, but we don't remove them when we acquire the data. We remove them after the fact. So that's these magnetic field distortions. So a magnetic field, like the main magnetic field of the magnet is like just these nice parallel lines. You can just imagine going through the bore of the magnet. And once you put something in there, those lines get distorted. And if that thing is not a perfectly made sphere of water, then those lines get distorted more. So you can imagine, like, say you had like a sphere of water, and then you put like a bone in there, or you put in an air pocket, wherever there's these boundaries and the different materials like air or bone, the magnetic field penetrates those differently than water. And so that causes signal to move around in what we call K space, such that signal can get piled up, or signal can also just be like eliminated, or resulting in like what we call signal dropout. Both of these things can be influenced by the slice thickness and the echo time. So if you want like really, really super thin slices such that you had no signal, there'd be very little distortion, which would not be good. Or if you go really, really short echo time, there would be less distortion, but again, there's not enough bold contrast in those, which I'm not going to talk about today right now. And then everybody's brain is different. So we have to have methods to sort of like take the shape of our different brains and so like morph it into what we call the standard template or standard space. Those things though are can be study dependent. So you might not want to say use a adult 40-year-old brain to morph or warp all of like your adolescent brains too. And you might not want to use that 40-year-old brain, say, to also warp all of your say Alzheimer's disease brains too, because they're very different. But you still kind of like want to have your group into a common template. So in the past, sometimes you would even maybe make your own template for your study and then report that. So the different types, first, before I go on, yeah, so I was going to ask if there were any questions at this point, because I know I'm kind of like moving along with like no pictures versus like just words, and there aren't going to be that many pictures. There's a few, but not that many. Any questions? No? Good. Yeah. Okay. We're good. Okay. So this is an order that like my lab in the past, actually more recently, that we do our pre-processing. But each one of these is sort of like a kind of like a scientific decision to make on the order that you do it and on whether you do it or not. So we do despiking. So what we do is we go through, and there's a question of like how you do despiking. So one is you can replace that volume or that slice. So say you have like a brain like here, where there's some bad data up here. Like you can see like it's dark up here and it just looks really whacked out. One way is you can take the time series data, so like before and after, and interpolate to replace that data. Or you can remove the data, just like cut it out. So like just like you're on a film editor and you just like drop those frames. Or you can leave it in and account for it in your statistical modeling. And again, like it's I don't know, for me, it's not very clear cut, like which way is like necessarily the best way, because there's no such thing as gold standard data for activation, because it's like we have to take the data to understand what's activating. There could be iterative ways to determine it, but anyway, so a despiking or somehow regression is what we typically do. Then we do motion correction. So what can happen is when you got your data, and here I've just simulated like a brain kind of like moving in the scanner. So here is this person, they're kind of like rolling their head around, kind of bobbing it around. And if I'm interested in like, say, some activation, like, I don't know, like let me just do it like right here, right? My model doesn't track the brain. The statistical model sits on this given voxel, and the data are moving in and out of the voxel, right? And so if I'm trying to understand activation there, it's just going to get smeared out, and I won't get any signal, no statistical signal. So what we do is we motion correct, or we take the volume, and as a rigid body, just think of it like my phone, right? If here's my phone and I want it like this, I just like brute force rotate it. Or if it's like translate it, brute force translate it, and then write out some new data. So then there is what we typically do is we acquire some what people call field maps. They're actually distortion fields or distortion images. A field map's a very different thing than what is typically covered. And we need to somehow like correct these distortions. So let me show you what these distortions look out like.
Are these for rest task or both?
The what?
Are these for rest task or both?
It doesn't matter. Okay, so here is a typical like image that we acquire, a very fast image. So here's the brain, a high resolution image of the brain. Oh wait, yeah. So I'm sorry. Yeah. So these I do this for like both. I'm doing like this set of steps for both. Again, there are, and I'll show at the end, there's some papers that like have looked at various different ways to like do processing. There is, again, like I said, like no true gold standard. One paper I read the other day was, they say, and it's a group, I think a Canadian group, they say, process your data different ways and report all different ways that you process your data. So we can understand the variance of the result based on the processing that you do. Yeah, so here's like some distortion maps or distortion fields or distorted images. So again, like here's what the brain should look like. Nice high resolution brain. Here is what we actually acquire. And so you can see like this doesn't look like what we had. And it's because there are these changes in the magnetic field, and the way we acquire the data are also sensitive to those changes in the static field. And it's mainly because like there's big air pockets by your sinuses and your ears, and there's bone, and that just distorts the field that then results in. Lucina has like a person with her.
I'm at my sister's house, so these are the
Okay.
nieces.
Okay.
Very distracting, I know.
So anyway, so we want like our data that are sensitive to activation to look like the person's like actual brain spatially. So then if we're gonna try to mold everybody to look the same, we want to be doing that step based on their structural image or this high resolution image, and not necessarily on their these activation sensitive images, because there's lots of distortions. So what we can do is, if we can actually acquire data that are sensitive to distortions in two different ways, and for those of you who are like hopping on the scanner, there's this thing called phase encode direction, and we typically acquire the phase encode direction in the AP axis, but it might be like A to P or P to A. And based on the direction that you acquire those data, and I can go into that in more detail in like a physics talk if people are interested. If you acquire the data stepping through phase encode space in one way or the opposite way. And I'm not talking, not talking right to left and then A to P, but I'm talking A to P or P to A, the distortions look different. So this one on the left is that the data were acquired in the P to A direction, and the data on the right is the same brain with the data acquired going A to P in the phase encode. And so you can see like these have greatly different distortions, but from those, we can estimate what type of distortion would give rise to these resulting images from some unknown common image. And so like iterate to calculate the mathematics to take you from this bad looking image to what it should look like to be in concordance with the anatomic image. So that can happen. Let me just like hop to it. And so here I've applied it to that image. And so now you can see like it looks much better. And I'll just put these in side by side. So here is the original image that we acquired. Here is the person's brain, and then here is the corrected image. And so it just looks, you know, shape-wise, with locations of the ventricles, some major like white matter structures and things like that, looks like the person's brain. These corrections, though, will never, ever, ever recover signal for you. It will just help move signal around. But if you've got a whole bunch of signal piled up, it's not going to like unpile it into the right locations. It'll just kind of like stretch it out. Or if there's an area of the brain where there's so much artifact that the signal's just dropped away, it's not going to recover that for you. Those you try to do things by maybe going to a slightly shorter echo time or slightly thinner slices. And I know that we've have tried to explore that for one of the studies out there. So now let me get back to the list. Okay, so that covers like this distortion correction thing. Now, the reason I do it in this order is if the person moves a little bit between when we acquire these images that are sensitive to distortion to actually when we acquire their time series data, I kind of want those to line up. And I also want to apply the correction to all of their time series data that's also been lined up. So I line up the time series data first. I then will take the distortion images and move those, what's called co-registration, into what is the motion corrected time series, and then I can calculate the correction. Now, caveat, all of these steps interact with each other. So motion correction works perfectly if there's no issues with like slice acquisition time. So if we could acquire all the data instantaneously, then motion correction should work relatively well. However, because it takes time to acquire the data, it's very possible that if the person's moving very rapidly, then the data in that one volume is somehow maybe spatially replicated. So you can imagine like you're acquiring this volume and you're stepping through, we'll just do the simple example of like going from the bottom to the top, not multiband, but just like going through like very slowly from the bottom to the top. And imagine this is the brain. And I start acquiring, and like right when I hit this slice, I move my head really rapidly. I end up acquiring that slice again. Okay. And so the chances of that happening are pretty small, but all of these things interact with each other. So that's why there's no necessarily like perfect order to apply these corrections, but this is just like one order that I heuristically argued to myself a year ago on why it should go this way. And I'd have to look at my notes to figure out what the argument I made to myself. Okay. But we did find at least that taking these distortion maps and making sure that they were in truly the same space as the time series data and then applying the distortion does seem to help when you look qualitatively at the resulting image. And this was, we were looking at like some ADME data. And the distortion fills were different. They were actually field maps. But anyway, here and there. The next one is slice timing. So again, like, it takes amount of time to go through and like acquire the data. And I have it in square brackets because of a point here to make. Just hop to it. Okay, so I'm going to hop to here really quickly. Actually, let me do this one. So if we're acquiring slices, so here's like a brain that we've acquired, and I'm putting in like these slices I've acquired, these red lines like that are going, like these horizontal red lines that are increasing in the Z direction, say, or the foot to head direction. And I've displaced them a little bit to demonstrate that they're not all acquired at the same time. And what I would like to have is them all acquired at the same time. But we don't have that. However, we've got data before like some event and after the event and during the event, right? So I've got like this volume with all the data, so like acquired like this, and then another volume with all the data acquired like that. If the person doesn't move, again, because these things interact with each other, I could do a temporal interpolation and making some assumptions that like signals are moving kind of slowly and move the data in time, such that it then would be as if we acquired all the data simultaneously. Now, why do we want to do that? When sampling rates were lower at like, say, a 2-second TR, then what happens is if I have like a true signal of activation, which is this black dashed line here, okay, and then I'm acquiring data, well, the first slice is this red one. It kind of comes, and the definition of 0 is arbitrary. So I've got 0 kind of like defined as in the middle. The red one kind of comes early. The black one, which is the middle slice, comes about right on time. And then the blue one comes late because you're acquiring it after the event takes place. So what we want to do is we want to like line those up. So if I do this interpolation, then the data in slice 1 is so like temporally locked to the middle slice and is temporally locked to the top slice. Now, that helps with like making our signal, like being more sensitive to our signal, so that so Lucina, when did they recommend that?
I remember that, when you hover over the FSL GUI, it gives you these like recommendations.
Yeah.
So I remember this was like 14 years ago, honestly, that there was like a note under slice timing correction that kind of explained all of the different things you were talking about. But also at the end of the day, it kind of said like, for all these reasons, we're not even recommending it. I don't know if anyone else remembers that.
Yes.
But it was,
So I do, and it's because they had a bug in their code. Okay, so I actually had a poster at Human Brain Mapping about this, that in their code, they actually were doing the slice timing correction in the wrong direction. So instead of like moving your data together, they were taking it further apart, right? So I like did all this investigation, checked exactly what version of FSL had screwed up, like, simulations showing that like you could actually get false activation, that you get false results because of it, like they would be displaced. Told them all this, and they came back going, yeah, we knew. and when they sent out the version, all they said was that slice timing correction was now more precise. They did not acknowledge that they had messed up.
so that's really interesting because I didn't know all of that. So now, if you do use their version of slice time correction, you believe it's doing the right thing?
So I still don't use theirs. I use SPM slice timing because SPM can handle multiband data, where I don't know if their slice timer can handle multiband data or not. But here nor there, with so let me show you like the impact of if you had like a slow TR, why to do slice timing correction. So, and I know I'm like giving people information that you don't really need to use anymore, but at least trying to like give some history of this. So if you acquired data, say I acquired a motor, a resting state, right? So the person's in the magnet doing absolutely nothing. And we know from observation that the time signals of the bold data in their left and right motor cortex seem to be correlated in time when the person's doing nothing. So we call that connected. And if I acquire this data in a sagittal view, so instead of like normally like we acquire like from the bottom of the head to the top of the head, but in this experiment, what I did was I said, let me acquire the data from the right ear to the left ear, such that by the time I got to the other side of the head, it was 2 seconds later. And then look at this connectivity or correlation signal or the signature between the two motor cortices. So here on this right-hand side one, I think I dropped a seed here in the, this would have been probably the right motor cortex because this is radiologic. So I would have dropped a seed here, and then this is the connectivity to the other side. This is with no slice timing correction. If I slice time correct, and this is again with like a slow TR of 2 seconds, then I actually get stronger signal in the connected cortex. Can do the same thing looking at, say, the default mode of I can acquire the data, this time in a coronal view. So here I've got a sagittal view showing how like the coronal slices are going through. And I can drop a seed again in the PCC and look at what is the connectivity up to the medial wall, the frontal medial wall, which we know is part of the default mode. And with no correction, meaning like it takes it takes 2 seconds to go from like the back of the brain to the front of the brain in terms of acquiring the data. Then with no correction, the data in the front kind of get out of sync. And so therefore you don't have a strong correlation. If, however, you do the slice timing correction, then you get a stronger signal in the front part of the brain. And this is also a function of the frequency of the signal. So you can imagine a very slow frequency signal is going to kind of stay connected because it doesn't change much over like the 2 seconds, where a very fast moving signal does change a lot over 2 seconds. So this is an argument of why you do slice timing correction. And in fact, what I cut out of this was the what happens when you do it the wrong way, which is what FSL had done for a while, and that you end up making the data even more out of phase, so you lose actual signal. But I wasn't going to add that, except I should have retrospectively with Lucina's question. However, this is all with like a relatively fast. There's all with a relatively slow TR of like 2 seconds. And modern systems, because we're doing, modern systems, because we're doing multiband or simultaneous multi-slice, the TR is typically on the order or less than 1 second. And so you don't really need to do that much slice timing correction. For some projects, we still do. You don't typically acquire data like this anyway. So it would be more of if there was, for some reason, you were interested in networks that were spanning the foot to head direction. And you felt like, oh, I want to really maximize that signal or that statistic, then you would do slice timing correction. And even then, for like a slow TR, the head's not that big foot to head versus it is like front to back. So it's a little bit less of an issue. And this is sort of like, and I'll make these slides available. This is kind of like demonstrated here is phase shift has to do with like how far out of time you are with respect to the slice timing. So if you're at 0, that means that your two signals are perfectly synced. So if like everything was going super fast with acquisition, say your bottom slice and your top slice were acquired simultaneously, then they have what we call 0 phase shift. If, however, they're so like out of sync, then the more out of sync they get more phase shift. Oops, sorry, this is very sensitive. But then that's also a function of like how fast these signals move. And so very slow signals, and this is the typical band of resting state, the very slow signals don't move, they don't oscillate as fast, and so they're less sensitive to the slice timing difference, where the high frequency portion of the bold signal for the resting state is going to be more sensitive to it. But again, I don't think for purposes of multiband, it's not necessarily that important, though this might be something I might be interested in just testing out, or if there's a way to do it. Okay, so let me go back now again to our list. I'll just do it this way. So they got the slice timing. So that's why I have it in brackets, because it's not critical to do, especially because if you're doing activation studies, the bold response is relatively sluggish. It takes on the order of a couple seconds for it to come to peak, and then it takes a number of seconds for it to like die down. And if you're doing a block design or block paradigm manipulation, then it's even less sensitive, because you're sort of like activating the brain for like 15 seconds and then letting the brain get back to rest. And so exact timing is not that critical with respect to the signal inside a single volume. So that's why I have it in these brackets.
Another thing with the slice timing is I think people need to be aware of how they acquired it. You can't just push the button on the GUI, because
No. Yeah. You should always, like, in fact, I would encourage everybody that when you are building your paradigm, that you, this is very true, Lucina. Sometimes we don't know how it was acquired. I will give an anecdote about like the ADNI data set. A lot of the ADNI data that we're analyzing for ADNI 2, so that's the Alzheimer's Disease Neuroimaging Initiative. The majority of the resting state data, if not all the resting state data in ADNI 2, is being acquired on a Philips, and all it says is that the order is default. So you have to know what default means. So if you have access to a Philips, you can understand what it means, but it's not clear, right? More modern systems hopefully have the timing of actual each slice that's been acquired, and those come out in like, so if you're using like the DICOM to NIIX code from Chris Reardon, it will write out a thing called the JSON file that then has like the timing in that will tell you like the time that each slice was acquired. But it's not guaranteed, because it's not a requirement for it to be inside that file. Because again, a lot of the stuff that we're interested in research has no clinical impact, and so they're not really necessarily, the vendors aren't necessarily interested in having to like change lots of code to like appease, a few thousand researchers. But very good point. But so what I was going to say is, when you're at the scanner and you've built your protocol or you're utilizing a protocol, always save it to PDF and then keep a copy of that, because that is documentation of your experiment. And if you modify your protocol, say halfway through your experiment, you need to keep a copy of your previous protocol and keep a copy of the new protocol. And typically what I do is I will just like populate my folder on the scanner with like my project, and then I'll have, so like I've got this Radco project where I will literally just embed the date of when I built that protocol. So it'll be like year, 4-digit year, 2-digit month, 2-digit day, no spaces. That way I'm like, okay, that is like the protocol. Don't use things like final protocol, because final doesn't necessarily mean anything, because then you have to say like the final or the truly the final, right? Final two, right? Yeah, it just, embedding dates in names is a good thing to do, but always try to keep that information. And yes, so sometimes maybe better to just skip the slice timing correction. Okay, so the other then is the need to register the high resolution image to the time series data. So that at some point you can either, if you're looking at individual activation maps, you can lay it on top of their anatomic image, knowing though that the EPI image does not necessarily have the same spatial fidelity as your high resolution image. And in particular, let me like this one here. You know, if people tell you that they've got like activation in the OFC, don't necessarily believe them, because this is an area right here that just gets blown out. So always, like, instead of like looking at your activation on top of the anatomic, which you can do, but also sometimes look at the activation on top of the actual mean time series data to understand like where you actually have signal or not. So you can understand like, do you believe it or not? I once like was doing some pre-surgical planning at Michigan 20 years ago, and you know, having some activation for temporal lobe and showing all these images to the neurosurgeon, and she's like, hey, we're gonna enter the brain to like this direction, blah blah blah. I'm like, yeah, wait, like these images that you're seeing are not actually representative necessarily of the anatomy, just because of distortions that no matter what, we can't remove all distortions. Okay, so let's get back then to, where was I? Yeah, so registering the anatomic data such that it's in the same space as your activation data. And then there are two like main camps. One camp does statistical analysis in what we call native space, and then the other camp does statistical analysis at this individual level at the in M&I space. And I was talking to Martin about this just recently, Martin Monty, and he said that they actually looked at this. Was there any difference? And there's not really any difference. There's some arguments for doing one or the other. I end up doing the SPM camp, because then if I want to do a whole bunch of different models, the data are already in M&I space, or if I'm doing connectivity, all of those outputs are already in M&I space. And I'm just historically not been a big FSL user as much as I have been a SPM person. But in either case, you have to warp the data then from their subject space, whether or not you're warping time series data or an activation map from the subject space into what we call M&I space, or the Montreal Neurological Institute space, or if you build your own template into that space. And that typically will look like this is just an SPM output. So here I've got like the person's brain has been warped to M&I, and then their bold data has been warped to it. And then another step that sometimes people do, sometimes people don't, is actually spatially smoothing your data. And the argument there is, just like we are collecting a whole bunch of time series data to sort of like do signal averaging, and that we're interested in like, so like matching a filter of the activation to what we expect the model of the activation to be. there's also argument to smooth your data to help get rid of noise fluctuations spatially. But if you overly smooth your data, then you will end up removing your signal or diluting it so much. So it's a trade-off on smoothing or not smoothing. And again, like that's like a decision to make. And it's also based on like how big of a spatial extent you expect your activation to be. Let me go to, so I'm just going to put up some, and I know we're almost out of time. So, and I'll make these available again. Like, so these are some papers that have to do with like processing for resting state. And this group, Alex Fornito's group with Lyndon Parks, they did a whole bunch of different pipeline evaluations. Tom Nichols has done some pipeline evaluations. There's this question or not of like with resting state data, whether you delete data or you keep it. I'm in the camp of keep it. There's this paper from the NIH that it talks about ways to process the data such that you can keep the data. And then once you start moving towards like statistical, yes, we can add those from Ted's group as well, Lucina. Once you start like getting more into like the statistical pipelines or analyzing some data, you have to be careful how you regress out things such that you don't necessarily, you don't naively regress things thinking that you've removed it, and once you've removed it, it never will go back. There's actually ways that you actually can accidentally reintroduce some artifacts, and so Martin's group wrote a paper on that. So then finally, the different pieces of code, like I have like evolved my own pipelines using various different pieces of code. So I end up using 4 different packages at this moment, sometimes 5 if we're doing surface activation data. So if I'm doing volume data, we use AFNI to do despiking. In the past, I've used McFlirt, but then changed that to SPM for doing motion correction. In the past, and actually I sometimes still use FLIRT for doing co-registration of, like, say, anatomic images into activation data, or these distortion maps activation data. For doing the distortion correction, I actually use this other package called Anima that seems to do actually quite well. There are also ways to do distortion correction when you don't have anything that measures the distortion. And we've used those methods based on ants that seem to actually give really good results as well when you are missing the data that let you know the sensitivity to distortion.
Oh, but you can do that without a field map or anything?
The what?
You can do that without a field map?
Well, if you have no field map and you have no distortion maps and you still want to undistort, there's a way to do it. Okay, if you have a T2 image.
Interesting.
Okay. And we've actually found, we've used it for diffusion data, and we found it very, very useful. Like, it just rocks. You're like, wow, this is really good.
Okay.
Yeah. But again, like, you're never recovering signal. You're just kind of moving things around to make you believe it's in the right spot.
Yeah.
Okay. In the past, we've used slice timer, but because of that problem, I kind of like moved away from that. And then a group in Vienna introduced a package or a module for SPM for doing multiband slice timing correction. So again, like, brackets on whether you use it or not. For registering, and in FSL, all of this happens, so like through the GUI. I haven't used it necessarily that much, so I don't necessarily remember. But for registering like the high resolution image to the time series, again, like either FLIRT or CoReg. And then and again, like, I don't know if there's like more modern methods in FSL, and SPM was always changing like their algorithms with respect to like how they do normalization. And they seem to get slightly better. But we use ants for doing normalization to MNI. It seems to really rock, seems to do a really, really good job. But if I'm interested in doing segmentation, yeah, I've got like the F nerd right here. We've seen it on the bottom here. If I'm really interested in doing, like, say, resting state, and I want to do a correction method called comp core, where we say we don't collect physiological measures of like heart rate or respiration, but I still want to correct my signal from those, then I can maybe derive it from the CSF or the white matter, and I need to segment the brain. Then I found that SPM does a really much better job segmenting into gray, white, and CSF than, say, ANTS does. But ANTS does a better normalization. So I will use a weird combination of all of these to sort of like drive my best end result pipeline. And I think that is it. And I hit 59 minutes. Okay. Any questions? And I know this was a lot. I will like maybe add a couple more notes, and I'll add those papers, Lucina. And then I'll push this out to the group, just probably through Slack or something like that as a PDF.
Yeah.
Then
I'll
people more than.
post something.
Oh yeah,
This
yeah,
is- Yeah, this is a great overview. Thanks. I mean, the idea is for the group to let us know the kinds of things you want to see more of. More intro, more advanced stats, more debates about pre-processing pipelines. So, send us notes either by email or through Slack so we can do these things in a way that we wanted to start kind of with the basics, but we can ramp up very quickly if people want to. So please do give us some feedback.
Anybody have questions in the chat anymore?
I think that's like,
Yeah.
yeah.
All right.
Okay, great.
Thanks, everyone.
Great.
Thanks, Robert. Thanks, Jason.
You're welcome.
See you all later.